Hello again, and now we'll look at the summing amplifier in part 2. The summing amplifier is a small circuit we draw like this. The op-amp with a feedback resistor to the inverting input, and we have two signal sources. The name says it sums these voltages here, V1 and V2 together. And the output voltage will be the sum of this gained up compared to the resistors. But for this small analysis, we want now to find an expression for Vout. And we use the same steps as before for the inverting amplifier, because this one, if we look at it, the signal sources are actually coming together here at the inverting input. So it could have an indication of that there is some signal inversion. But we just run our analysis step through to find the expression for Vout. Again, the first thing is we assume that the op-amp is ideal. And so we can use rule 1 that states that the raw gain of this amplifier here is infinite. And for rule 2 that the input resistor between these 2 points here, the inverting input and non-inverting input, is infinite. And the output resistor here is 0. So we don't have any loading effects in the op-amp, because it also have a voltage dependent voltage generator here, and have normally, when it's not ideal, a small output resistor. So when we pull a heavy current here, we will also get a voltage drop inside here. But for now, it's ideal. The output resistor is 0. Then rule 3 states that the current going into this pin or out of it, depending on what could go, is actually 0. So no current running and nothing is stealing current from this point here. The next step, step 2, is we have to look for negative feedback. And we know we have to have something from the output feed it back to the inverting input in order to have negative feedback. And we look, yes, we have negative feedback. So we can apply rule 4. And rule 4 states that the voltage on the inverting input minus the voltage on the inverting input and the non-inverting input, the non-inverting input voltage minus the voltage on the inverting input becomes 0 when we have negative feedback. That's rule 4. And that means we have a summing point constraint here, that this potential, we will also see that potential here at this pin. So we actually have ground level here. That's important. Because when we have ground here, this one don't affect this one. So this one current here will just look like that it looks into ground, and the current coming from V2, E2 will also look like it comes to ground. So they are independent here in this analyzer. That's really nice. So we can sum the currents in this node by Kirchhoff's current law. So E1 will go to this point, and E2 and E3. And we can write this small equation, E1 plus E2 plus E3 is 0 in this point. And since the output here is connected to the feedback resistor, and the E3 is related to that. This is moved to the other side of the equal sign, because here this is the interesting part for us. So the next step is to write voltage expression so that we find a value for the current. And we know we have ground on this point, 0 volt here. So V minus is 0 and V plus is also 0, connected to ground, and we have negative feedback here, so we will have the same potential here. So by writing the equation, we get E1 equals to V1, that was the signal source, minus V minus over R1, and because V minus was 0 volt, we end up simply having V1 over R1. And for the small V2 source and E2, it's the same setup because of this ground level here, and we get an expression for E2 that V2 minus V minus over R2 simply gives V2 over R2. The E3 current is generated because of the voltage drop from V out compared to V minus at 0. So we can again write an expression for the current that becomes E3 equals V out minus V minus, so that's 0 here, over the feedback resistor. So we get V out over the feedback resistor. And finally we have the equation and can put in our expression from it and solve for having V out on the one side of the equal sign and an expression of voltages and resistor ratios on the other side. So the E1 current was V1 over R1, and E2 was V2 over R2, and E3 current was V out over the feedback resistor. But here we have this sign, so we have to remember it. Now I move the feedback resistor up here, so we get the ratio of resistors, and we have now isolated V out, but I don't like the sign here, so I will move it, flip it over and write V out equals minus and have a branch having V1 times the ratio of the feedback resistor and R1. So the gain for V1 is simply like for an inverting amplifier, the feedback resistor over the resistor sitting with the source, and V2 is gained up by the feedback resistor compared to the R2. That also makes sense. This looks also most equal. If we put my fingers here, it actually again looks like the inverting amplifier. So we get an expression of V out having this expression. If we assume that this ratio is 1 and this one is also 1, so they could be 10 kilo over 10 kilo. Yeah, well then we get 1 here. And then V out simply is the signal source 1 plus the signal source 2, but with sign inversion. So we sum them, but also invert them. Well, this is not always nice, but at least we have something. But how could we make a circuit that we get rid of this sign? That could be good, so that we just have a circuit that can sum V1 and V2 without sign inversion. But for now, the summing amplifier has a sign inversion because it's based on the inverting amplifier setup. But let's look at a circuit where we actually get rid of this inversion sign. And we just combine two circuits now. We can combine the summing amplifier here with the inverting amplifier, because the inverting amplifier has a sign inversion and our summing amplifier also has a sign inversion, and when they are timed together they disappear, so they cancel out. And if we are smart and making an amplifier with 1 times 1, here we get 1, then we simply have the summing amplifier ratio between these, the feedback ratio and R1 sets the gain for V1, and the ratio, the feedback resistor over R2 sets the gain for V2. And then we have no sign and we really sum them, but we need 2 op amps and 5 resistors to do that. But that was simple. So this is how we actually cascade circuits together to get the function we like to have. And here we use the inverting amplifier to get rid of this sign here. That was very nice circuit. Yes, this was part 2.